The idea of force is fundamental to much of the work in mechanics, and in this video we are going to introduce some of the important basic ideas about forces. So, if a man is pushing a crate across the floor, then we say he is exerting a force on the crate, and we can represent that by a simple diagram where we show an arrow to represent the force, with the direction of the arrow representing the direction of the force. If the man now ties a rope around the crate and pulls the crate across the floor, then the crate is being pulled to the left by the force in the rope, which we'd normally call the tension in the rope. And we can represent that in a diagram. If the man now lifts the crate off the ground and holds it still, then the crate will experience a supporting force from the man's arms going vertically upwards, and we can draw that in our diagram as well. Now, there are lots of different types of forces, some of which we don't use in mechanics at all, but the ones that we will be using in mechanics are principally the weight, and the weight of an object is the force of gravity exerted by the Earth on the object. The weight of the object acts through the centre of mass of the object. If a body is being pulled by a string, or spring, or chain, then the body is being pulled by the tension in that string, spring, or chain. Similarly, if a body is being pushed by a compressed spring or a rod, then it is being pushed by a thrust in that spring or rod. The engine of a vehicle produces a driving force that actually propels the vehicle along. If a body is in contact with another body, then there is always a contact force between the two bodies. It's usually split into two parts. A normal reaction, or normal force, which is always present and acts perpendicular to the line of contact between the two objects. And a frictional force, which acts along the line of contact between the two bodies if the contact between the two bodies is not perfectly smooth, and there is some motion or tendency towards motion between these two bodies. A special case of frictional force, which is important within mechanics, is the idea of air resistance, which can be regarded as the frictional force between a moving object and the surrounding air. In many examples in both this module and in Module M4, as part of the modelling process, we'll assume that the air resistance is negligible compared to other forces. This assumption is reasonable if the motion is taking place in a vacuum, or if the object moving can be regarded as a particle, or if the speed of the object is low. When dealing with the motion of a vehicle, it's quite common to combine the frictional force and the air resistance forces to produce a single resistance force that acts in the opposite direction to the motion. Now, the next thing we need to consider is the effect of a force. Let's consider the effect of a single force acting on a small block which is resting on a sheet of ice. If the force applied to the block is horizontal and acts through the centre of the block, then we would expect the block to accelerate to the right, and we would also expect the size of the force to affect the size of the acceleration. If the force applied to the block is horizontal and does not act through the centre of the block, then we'd expect the block to accelerate to the right, but also to rotate a little bit around the bottom right-hand corner of the block. If the force applied to the block is vertically downwards and acts through the centre of the block, then we'd not expect any motion at all unless the force was so large as to deform the block or crack the ice. If the force is applied obliquely to the block, then the block would be expected to both slide and topple a little bit. Now, from all of these examples, we can see that the effect of a force on a body depends on the size of the force, the direction of the force, and the point of application of the force. Force is therefore a vector quantity. It has both size and direction. The size of a force is given in newtons if we are working with the SI unit system, and for the moment think of a newton as being approximately the weight of an apple. We'll get a proper definition of a newton later on. Now, it's really important that when we're considering mechanics that we are able to draw decent diagrams showing all of the forces acting upon a particular body. So, if we want to show the forces acting on a block which is resting on a horizontal table, then we've got the weight of the block acting vertically downwards, and we have got the reaction of the table on the block acting vertically upwards. And this is called a normal reaction. It's at right angles to the line of contact between the table and the block. There's no frictional force, since there is no possibility of the block moving in any direction if the block is simply resting on the table. If we've got the forces acting on a particle which is at rest on a rough inclined plane, then we represent the particle by a small circle or a small rectangle, and the forces that we've got acting are the weight of the object acting vertically downwards, the normal reaction between the particle and the plane, and the plane is exerting a force out of the plane onto the particle, so for coming vertically out of the plane, that's the normal reaction. And then there's going to be a frictional force because it's a rough plane, and that frictional force will be opposing the possible motion of the object, and the possible motion of the object in this case would be down the plane. So the frictional force is acting up the plane. If we've got a car travelling up a hill inclined at 8 degrees to the horizontal, then we're going to model the car as a particle. Then the forces that we've got acting are the weight of the car, we've got the driving force produced by the car's engine, we're going to have the normal reaction of the plane on the car. Now, in actual fact, of course, the car is touching the plane in 4 points, which are the tyres. So there are in fact 4 different normal reactions in real life. But since we are modelling the car by a particle, we just draw one normal reaction in, which is the sum of the 4 different normal reactions. And then there will be the resistive forces, which is a combination of the air resistance and the frictional forces, and this will act in the opposite direction to the motion. So because the car is moving up the plane, the resistance forces are going to be acting down the plane. For the next example, we're going to first of all show the forces acting on a small stone after it's been dropped from the top of a tower 20 meters high. And we'll certainly regard the stone as being a particle. The speeds are going to be relatively low, so we can ignore air resistance. So assuming that we're ignoring air resistance, the weight is the only force acting. So there's my completed force diagram. On the other hand, if we've got a free-fall skydiver after he's jumped out of a plane flying at an elevation of 3,000 meters, then he certainly isn't a particle. There's certainly going to be a considerable air resistance there, so the force diagram in this case would need to show both the weight and the air resistance, which we've denoted by R. Now, when we move on to more complicated systems of objects, we will frequently have to draw the forces acting on the complete system or the forces acting on parts of the system. So when drawing a force diagram for the whole system, we only need to show the external forces acting on the system. The internal forces acting between parts of the system are ignored, since Newton's third law tells us that these forces are equal in magnitude and opposite in direction, so will cancel each other out. But when we're drawing diagrams for the components of a system, then we do need to show the internal actions of one component on another. Newton's third law tells us that if component A exerts a force on component B, then component B exerts an equal and opposite force on component A. So, for our final example, we're going to consider a car which is pulling a trailer along a horizontal road. We're going to draw separate force diagrams to show the forces acting on the whole system of car and trailer, the car only, and the trailer only. So, for the whole system, first of all, the forces that we've got acting are the weight of the car and the weight of the trailer, the driving force produced by the car's engine, the normal reaction between the car and the road, and the normal reaction between the trailer and the road, and then the resistance to motion of the car and also the resistance to the motion of the trailer. Moving to the car alone, the forces acting on the car alone, we've got the weight of the car, we've got the driving force, we've got the normal reaction between the car and the road, we've also got the resistance to the motion of the car, which is RC, but we've also got the force in the tow bar connecting the car to the trailer, and that will be acting to the left because we know that the trailer is going to be dragged back by the trailer. If we now move to the forces acting on the trailer alone, we have the weight of the trailer, the normal reaction between the road and the trailer, the resistance to the trailer's motion, and then we've got the force in the tow bar connecting the trailer to the car, which is pulling the trailer to the right, and will be equal but opposite to the force that the car experiences from the tow bar. So there we've got our force diagrams for the whole system at the top, for the car alone in the middle, and then for the trailer alone at the bottom of the page. That concludes our first look at forces. In the next video we'll be looking at how to deal with the arithmetic of forces.